I've written here two of the most famous laws of nature, known as Gauss's B law and Ampere's law. Gauss's B law should be compared with Gauss's electric law. Remember that the electric field, if B were replaced by the electric field, I would get the following statement: E dot dA is equal to the closed flux electric, and that would be the charge enclosed over epsilon naught. For some reason, Gauss's B law says that right hand side is always zero. In a sense, it tells us that magnetic charge always occurs in pairs of north and south. You can never have an odd number of north poles and an even number of south poles, for example. If you had that situation where there are more north poles than south poles, that would be like having more plus charges than minus charges, and you will end up with some net enclosed charge. Well, Gauss's B law dashes our hopes for monopoles. Unless a monopole is found, this law tells us that magnetic poles always occur in pairs of north and south. I mean, you already saw one of the reasons why this should be the case. Even a current carrying coil has got a magnetic moment mu, and that magnetic moment mu can be thought of as going from a south pole to a north pole. And current carrying coils are like atomic magnets. So if you have an hydrogen atom, you'll have the same situation there. The electron is going around a proton and it causes a magnetic moment. So even at the atomic level, you're seeing that you have a north and a south together. You can never have a north or a south by itself. But still, scientists are thinking about trying to violate the right-hand side of Gauss's B law. So basically, Gauss's B law says that closed flux through a surface is a useless thing to consider for a magnetic field. Later on, we'll see how the flux through an open surface actually gives us a lot of information, and that's when we consider Faraday's law towards the later part of this week. Right now, let's focus on the other statement that I made here, and that is the line integral, which means you have a single integral here, not a double integral. That's a surface integral. And this is a curve. Actually, it's a closed curve because I put the symbol naught over there, indicating it's closed. And furthermore, it's an oriented closed curve because I put a arrow too. So this should be thought of as something like that, but not quite, because on the left hand side you have a line integral and not a surface integral. But on the right hand side you do have something enclosed. So current is enclosed in much the same way as charge was enclosed in Gauss's E law, even though the left hand side has completely different meaning. So let's focus on the meaning of this integral and understand how to compute Ampere's law for a simple situation. In later videos, I'll show you how to use Ampere's law in detail. Let's just focus on setting it up. So the left-hand side is called the circulation integral. Whereas something like this is called the flux integral. So the flux integral captures the dot product information of the field with the unit normal times the area of that surface, whereas the circulation integral captures the flow around a closed loop. So the circulation integral, if you roughly think about it, you have here a closed loop. It does not have to be circular. It does not even have to be planar. In other words, it can come out and go into the page, but I cannot draw that, so I'll just draw a planar loop, and it has to be oriented, so it's oriented like that. And then what you do is you go around this thing. Now as you go around, the magnetic field is going to point every which way. We don't know, okay? It's going to point in all weird directions. In one of the homework problems, a portion of the homework problem for extra credit is for you to show me that you don't have the radial component of the magnetic field ever. and that radial component is removed using Gauss's B law. So after all, this law is good for something. It's good to show that the radial component of the magnetic field in most situations is 0. In highly symmetric situations, that is. So in other words, but let's not worry about that. Let's just take the magnetic field to be B. So we can write the total magnetic field to be a decomposition, and most of our problems will have some sort of symmetry, so we can use a coordinate system that's like a cylindrical coordinate system. So let's write this as a BR component, a tangential component, and a Z component. That would be a cylindrical symmetry, RTZ, where R is the radial direction and T is the tangential direction, and Z hat comes out of the page. So that's Z hat. So that will be our typical coordinate system setup for something like Ampere's law. Ampere's law applications include wires and ribbon cables, solenoids, infinite sheets of current, you name it. And in the later videos, we'll look at all these symmetries. But right now, I'm just interested in the setup. What does this tell us? So you go around this arbitrary curve that you draw, and ds vector is going to point tangent to this curve at every point. So obviously the angle made between B and ds keeps changing. And by the way, I drew the B also on the plane of the paper. It does not have to be. B has got this decomposition, which means that certain components of B can actually be sticking out. But whatever it is, you go around and you take the dot product at every step and you integrate it. That's what the symbol means. And you go in a specific direction indicated by that arrow. That's what that arrow means. And when you do all that hard work, what is left over? The answer is just going to be some constant of nature mu naught. This mu naught turns out to be 4 pi times 10 to the minus 7. It's the same mu naught that comes in Biot Savart law, Tesla meter per ampere. And here you can actually see the units come out really nicely, because that's Tesla, that's meters, and that's amperes. So that has to be the units. Times the current enclosed. Just like the charge enclosed in Gauss's E law, you have the current enclosed in Ampere's law. Let's actually use Ampere's law in a simple way to find the magnetic field everywhere of an infinite straight wire. There's an infinite straight wire, and I'll indicate it's infinite by putting those ellipses. And it's carrying some current I. Let's say the current is constant. Let's call it I naught. And you want to find the magnetic field everywhere in space. How do you do it? Now, of course, you don't know up front how the magnetic field looks. So let's pretend to be a little bit purposely ignorant. We don't know how the magnetic field looks, but how can we use Ampere's law? Well, Ampere's law tells us that the flux is the current enclosed, not the flux, the circulation equals the current enclosed times mu naught. So let's use that to our advantage. The best Amperean loop to choose in this situation is an Amperean loop that encloses the current like that. Okay, and that's perpendicular to the plane of the current. Now if I take a magnetic field, the Amperean loop like that, I don't really care if the magnetic field has other components. So let's suppose, for the sake of argument, this is not true, but suppose for the sake of argument that you also had a radial component of the magnetic field. Like I said, in the homework assignment, you'll show this is actually 0 using Gauss's B law, but let's suppose it's there. And let's suppose there's also a Z component to the magnetic field. Again, it's not possible because of infinite symmetry, but let's just say for the argument it's there. And also, let's suppose there's a tangential component of the magnetic field. And I'll draw the tangential component like that. Actually, you know what? I should have drawn it like this. BT. So I'll draw the tangential component in a way that respects right-hand rule. And here I'm only putting the arrow on the side that's coming towards me, that's going away from me. Okay, so let me remove this extraneous component here. Okay, so what's going to happen as you go around the Amperean loop, which in this case is a circular loop C, is that the Z component and the R component are going to be making an angle of 90 degrees with the ds vector. The ds vector is precisely the same direction as the B tangential component. So as you can see, ds makes a 90-degree angle with B sub r, and ds also makes a 90-degree angle with B sub z. So those components will not contribute when you take the dot product. Let's work on the left-hand side of Ampere's law for a moment. The integral along the closed curve C, B dot ds, will be written as the integral along the closed curve B radial plus B tangential plus BZ dot ds. And here's where you use the additive property of integrals and split it up into three portions. Br dot ds plus Bt dot ds. Each of these is still a closed oriented integral along a curve C. This curve, by the way, in honor of Ampere, is called an Amperean loop. Amperean loops are not necessarily circles. Later on we'll use loops that look like rectangles and so on. Okay, now let's do the reduction. This is 0, not because we know BR is 0, although it is, but it's 0 in this instance because the dot product is 0. So we'll put the 0 through the dot. And this is 0 for the same reason. And now we are just left with one term. Now by symmetry, as you go around the Amperean loop, you're always going to have Bt and ds to be parallel to each other. So let's write down the answer. So we can remove the orientation symbol now. I still have a closed curve, but this becomes Bt ds cosine 0 degrees. And now I can take Bt as a function of r outside the integral because it certainly is a constant all over the Amperean loop. So Bt as a function of r, and now I have this integral, which actually is something that you already know. So that's the beauty of Gauss's law and Ampere's law. You're left with an integral that you knew even before you came to RIT. So this is just Bt as a function of r times the integral of ds along a closed curve C. That's also called the circumference of a circle. The left-hand side of Ampere's law is always going to be this for all problems involving cylindrical symmetry. So things like wires with an inner diameter and an outer radius and an inner radius, like inner radius A and outer radius B, non-uniform distribution of current, like J as a function of R is the only possible non-uniform distribution I can give you to make Ampere's law of any use. We'll look at all that in later videos. So all those things have cylindrical symmetry. So the simplest case of a wire also has cylindrical symmetry. Once you have this result, you don't have to keep doing it. You can simply use it in future problems. And what I have now is Ampere's law is the following. It says that the circulation integral, so circ B, equals mu naught times I enclosed. Let's do that. Circ B, which was all of this left-hand side work, is just B of t times 2 pi r. So Bt as a function of radius times 2 pi r equals mu naught times the current enclosed. How much current is enclosed? Well, there's one issue. We don't know if it's positive or negative. So here's a right-hand rule for your benefit. If you take the direction of the loop circulation, so that's going to be, remember I told you the arrow was coming towards me. So if the direction of the loop circulation is encircled by your right hand fingers, then the thumb gives you the direction of positive current. Okay, so that's positive I naught. Done. Now we just have to divide both sides by 2 pi r, and I get Bt as a function of r equals mu naught I naught over 2 pi r. And that's the result for an infinite wire. Now, if you want a semi-infinite wire, I suggest you do the infinite wire first and then use the principle of superposition. Do not start with a semi-infinite wire and apply Ampere's law, because you won't have the infinite symmetry to help you deal with these components. So that's how Ampere's law is used in a simple situation, and in later videos we'll do more complicated problems.